Welcome to the SISAP 2021 conference here in Dortmund, where I'm sitting right now. And this is the presentation for the triangle inequality for cosine similarity. Let's first begin with the triangle inequality. That's a fundamental property of metric spaces, and it's a very, very useful property. Formally, it's very simple. The distance of x to y is less than, or at least at most as much as, the distance from x to z plus the distance of z to y. That intuitively means that we know the shortest path from x to y, and this distance measures the length of the shortest path. Any detour over some point z is at least as long as this shortest path. So for Euclidean distance, that is, as the crow flies, the direct connection between 2 points. And if we take a third point into account, the path usually gets longer. It can be as long, that's when we have equality, if the point is directly on the connection line. It can be significantly longer if z is in the wrong direction. So these are very similar cases. The way it looks geometrically depends a lot on a distance function that we use. This is with Euclidean distance, which is the simplest case, but we could also be using Manhattan distance. And then this is one of the multiple shortest paths. First go in one axis, then in the other. And again, we have a triangle inequality here. If we take a detour over some point z, it is at least as long as this shortest path. It could be equally long, and this time the point is not on the connection line of these points, but it is in like the hull of this rectangle of the points. Then there exists this path where z is on the path and the length is equal. So interestingly, for Manhattan distance, we have many more points where we have equality here instead of an inequality. Triangle inequality is a very, very useful property for any type of similarity search and for distance-based algorithms. There's a second talk here in this conference about accelerating spherical k-means, and many of the fast algorithms for k-means clustering, they use this triangle inequality. In indexing, we use it a lot in so-called metric indexes. They use the properties of a metric, and that involves the triangle inequality. Some indexes, such as the cover tree and the VP tree and the ball tree, they are based on like covering balls of an area. So given this data set, except the query point Q, I can cover it with balls that I use to partition the data, for example, to store it on a disk, as done in the M tree, or even just in memory only, as with the cover tree. And usually these structures will be nested if I have larger data sets. Now, if I have this query point Q and I want to find the nearest neighbors of the point Q, or whether, for example, all neighbors within a certain distance, then it's interesting to be able to process these balls at once without looking at all points inside. That can be much faster if I can exclude, for example, the ball on the right-hand side as being too far away outside of my query distance. Then I do not need to compute the distances to every point in there, but only to the reference point P1. So I'm computing only these two distances first, but that is only the distance to one point. But I do know the radius of this cover ball, and if I shrink the distances by this radius r, I get a minimum distance to this ball. And this minimum distance is obtained by using the triangle inequality. And now if the ball on the right, for example, the minimum distance is larger than the query radius that I'm interested in, I can discard this part of the data immediately. I can also similarly compute a maximum distance and use this to identify true positives. There are many ways I can use the triangle inequalities. But I do need a distance measure that has the property of the triangle inequality. And that is not universally true. A very popular distance function these days is cosine distance. It's probably one of the three most popular distances by now. Of course, Euclidean distance is very standard, and we have Manhattan distance that is also quite popular, but cosine distance is used in a lot of high-dimensional applications, ranging from text, similarity search on text, for example, but also in many of the neural network techniques. We're using cosine distance to measure the similarity, for example, of word embedding vectors and all this. Right now, a lot of the search in neural networks is done with a brute force comparison. But we would like to be faster than brute force. The problem is cosine similarity itself is a similarity function. It's not a distance, and I do not obviously have similar properties that I could use for pruning. So that's why people are using brute force search. Cosine distance measures intuitively the angle between the vectors x and y. So that's the angle between the vector from 0 to point x and 0 to point y. And this can be written in different ways. And the interesting property is that it relates to the dot product of x and y normalized by the length of the vectors. And if we have applications such as spherical k-means clustering, we can normalize all the input data when loading it, and then it's simply the dot product. But this is only a similarity function. It's not a distance metric as we would need it for indexing, for example, with the M tree or the cover tree. There are several variants of cosine distance. The first one is probably the most used one. If you call the function cosine distance in a standard toolkit such as scikit-learn, it likely uses this first equation because it's so simple. But the first equation is not a metric. It does not have the triangle inequality. The second one, taking the root of twice this function, is a metric. And the third alternative is using the arcos distance, sometimes is it called. This one is also metrical, as we will see. But all of them have a problem. So the first one does not have the triangle inequality. We can't use it. The second one is numerically inaccurate. Well, the first one is also numerically inaccurate. Both of them are pretty bad in this respect. If we have high similarities, we get catastrophic cancellation, and we have a very low precision in distances for small distances, which is a problem for search. So we don't really want to use either of them. The third one, it's much more accurate, but it's also much slower. Computing the arcos on a modern CPU takes several dozens, if not 100, ticks of the CPU because that's a trigonometric function that needs to iteratively be computed. We could use huge lookup tables to make it faster, but it's still one of the more expensive functions. It looks harmless, but it's substantial. So we don't really want to use this either. It's too expensive. So it would be nice if we would not need to go from a similarity function to a distance at all. What if we could just do everything directly with the similarity function? In these top two cases, we wouldn't have the accuracy problem. So that would be nice. And then we could begin with indexing with respect to similarity as opposed to current indexes, which usually index with respect to a distance function. But we will need a similar triangle inequality for similarities. And that's actually what we propose to use in this paper. So there are different ways of obtaining that, and the obvious way would be starting with the Euclidean distance. If we have this normalized data, then everything is quite easy to see, but it also holds for the general case. We know that cosine similarity in this square root version, cosine distance, cosine square root distance kind of, is related to Euclidean distance, except for the constant factor, it's actually equal. So we do know we can use the Euclidean distance triangle inequality and replace Euclidean distance with this transformation. And then we get essentially the first line inequality. And to avoid the square roots or reduce the square roots, we can square everything, and we can remove the sign to remove the 1 minus. Then we have the second line, and we can then try to simplify this function a bit, and we get the third line on the slide. So we have the similarity of x and y is the similarity of x and z plus the similarity of z and y minus 1 minus 2 times the square root. So we do now have a first triangle inequality for cosine similarity, which is actually a version of Euclidean, regular Euclidean triangle inequality. But it's kind of unconvincing because of adding up two similarities, which will result in a value larger than 1 up to 2, then subtracting 1 again. It's likely that this bound is not very good. It's not very cheap because of the square root. So we also looked into approximations of this. One approximation is given here. So we can take the smaller of the two similarities, and if we put this in the square root on the right hand side, we still obtain a bound, but we get rid of the square root. But we end up with this odd -3. So we add 3 similarities, subtract 3. It's kind of fragile, and it's not very good bound, actually. It's not a very good bound. So we looked into ways of obtaining a better bound. And we are working here with angles. And if you think of the geometry of points on a sphere, so if we have like a sphere here, and we have 2 points, and we are looking at the angle. If we look at Euclidean distance, we are looking at the direct line between these 2 points, which is called the chord length. But actually, we cannot travel this way on a circle. We can only travel on the edge, on the surface of the sphere. And that's actually what is measured by the arc length instead of the chord length. So there's good reason to say that this is more accurate. It will yield a tighter bound because this is exactly where we can travel. We cannot travel on the chord. So this does also satisfy a triangle inequality of based on the like a path on the surface of the sphere. So we do know that the arc cos of the similarity is less than the arc cos of the two similarities that we have, arc coses of the two similarities if we add them. And now we can try to get rid of all the arc cos functions. So we apply cosine to both sides, which flips the sign of the inequality. So we have the similarity is larger or equal to the cosine of the sum of the arc cosines. But that is still 3 expensive trigonometric functions to compute. It turns out that we can simplify this. The cosine of 2 arc cosines can be rewritten into the product of the 2 similarities minus this square root term that you can see here. And this is actually a nicer bound than what we had before. It's interesting to see that we do have the product of the 2 similarities in here. And the bound is a bit tighter, and we have less variance in the bounds because we have the squared similarities on the right-hand side inside of the square root. So that is closer. We also, again, looked into ways of getting rid of the square root, which is also a more expensive operation. So we have 2 more approximate bounds here, but both of them were not convincing in the experiments. So let's look at the 2 differences. So we have chord length, which is a Euclidean-based bound, and we have the arc length, which is the Arcos-based bound in the left 2 figures. And of course, the most striking difference is that the arc length-based bound is actually able to work with in the bottom left, right, which means if I have a point Z that is opposing my X, a vector that's going in the exact opposite direction, and it's also exact opposite of the direction to Y, then I know that the 2 points must be close because I don't have infinitely many room that is exactly opposing. But most of the time when we are working with cosine similarity, we are confined to the non-negative values. Then we don't have any vectors that go in opposite directions anyway. So let's for now ignore the bottom left part where we have the more visible difference and zoom into the non-negative area. Now we can see that the difference is actually surprisingly big between the two bounds. It can be more than 0.4 in difference, which is a pretty high value given that we are talking about similarities between 0 and 1. But it's largest in like the middle ground area of like both similarities being 0.6. If we are actually doing similarity search with this, we are most likely in the top right area of this. And there, the difference between the two bounds is visibly not very large. It exists and the relative difference is still substantial, but it's not as huge as it may seem in this plot. Nevertheless, one key result is that the arc length bound can be much better than the chord bound, and it's tight. So the chord bound is not optimal, but the arc length, since we're talking about working with the arcs on the surface of the sphere, the arc bound is actually as good as we can get. We can also derive an opposite triangle inequality. This is very easily obtained by rearranging and renaming variables. So if you take the standard triangle inequality, d of xy is less than d of xz plus d of zy, and you take one of the terms on the right-hand side to the left and then rename things, then you get a very similar triangle inequality where d of xy is larger than the difference between xz and yz. And this second bound is interesting to consider, for example, true positives. So you have a cover of candidate points, and with this bound you could identify all of them as being a result without checking the actual distances. And some applications also use the second bound, and we can obtain a very similar bound for cosine similarity, and it simply has the sign in front of the square root flipped to a plus. So this gives the interesting approximation that the similarity of x and y is approximately the similarity of x and y times the similarity of y and z. So that is kind of interesting, and it's also very easy to see that if one of the distances is of the similarities is very high, well, then this approximation becomes very good. If one of them is very small, then it gets very loose. So that is the new triangle inequality, and this version here yields good performance and better pruning power than the earlier approach. This is a simple benchmark to measure the runtime comparison as well as the accuracy. So we already looked at the accuracy before. This is the runtime. We did some Java JMH benchmark, so micro benchmarking with the standard tools for this. We have a baseline in here, which is just taking the sum of all the vectors. And we can see that Euclidean distance is slightly more expensive than taking the sum of the data, but it's not very expensive. The lower bound that we obtained is slightly cheaper, but much worse in accuracy. But if we go for the RCOS-based version, then we are like 600 times slower, 60 times slower. 60 times slower is quite substantial, despite having a good accuracy. If we don't use the CPU standard library RCOS, but a library that's called Java, it's only 6 times slower than Euclidean distance. But even 6 times slower than Euclidean distance may be a problem in some cases. With the new version that avoids the RCOS, instead only has the product and the square root, we are at a performance that is even slightly better than Euclidean distance. And this case is not even using sparsity yet. If we have sparse data, the difference is likely to be even larger. So we have a triangle inequality that is quite efficient to use. And yeah, it's not much more expensive than the standard techniques that we are already using, but now we can just work with the similarities with a high accuracy directly instead of transforming them into Euclidean space and using the worse bounds derived from the chord length instead of the arc length.